Yes, thank you, Deepa. I really appreciate that. Welcome. If you are not muted or turn off the mute, I really appreciate you doing so throughout the remainder of the event. I am really excited this evening to introduce Matthew Shetrone. Dr. Matthew Shetrone is our new Deputy Director of the University of California Observatories. He started with us last November, but he's been with the University of California system for much, much longer. Matthew received his PhD from UC Santa Cruz, and he has had a really neat life where he's got to live in a lot of neat places, starting with his education in Austin and Santa Cruz, and then for work moving on to Santiago, Chile, and then to McDonald Observatory, which is where he was before he moved back to Santa Cruz, which he calls home. He was mentored by someone that many of you will remember, Bob Kraft, and he's hoping to live up to his legacy here at UC Astronomy and working with the University of California Observatories. We're delighted to have him as our first Ask-an-Astronomer. And so the way that this is going to work this evening is I'm going to ask questions that you submitted on Facebook, on Instagram, on email, and then he's going to answer those questions later in the session. I'll do a lightning round specifically on black holes, which I hope that you will enjoy, and I will turn off these chimes as folks are coming in and out, but just wanted to show you how many folks are excited to be joining us. We're up to over 100 between Facebook and Zoom tonight.
Wow.
Absolutely. Wow. You ready to go, Matthew? You think that you can you get these questions answered for our 100 guests?
I'm quick in my boots.
Well, let's start, Matthew. A question that we received from Facebook from Marco Antonio Aloa. He asked, can I see the diamond of Virgo from Northern California? If so, which way and when do I look?
The diamond of Virgo. I really like this question because, you know, constellations are just made up things. And the neat thing about the diamond of Virgo is that only one, actually none of the stars are in Virgo. So there's a star in Canis Ventriculi, there's one in Leo. There's one in Virgo, that's Spica. And then there's Arcturus, which is in Bootes. So only one of the stars in the diamond of Virgo is in Virgo. But you can see it from Northern California, and you can see it tonight if it's clear. Let's see, it's kind of cloudy where I am. And trying to find it is kind of fun. So you go out and find one of the most recognizable things, which is the Big Dipper. So if you can find the Big Dipper, there's the handle makes an arc. And if you kind of follow that arc, keep arcing and arcing, you come to a reddish star, and that's Arcturus. And that's the upper left-hand side of the diamond of Virgo. And then if you, like a football player, spike straight down from there, you should be able to find another bright star called Spica. And so that's the left side of the diamond of Virgo. And so I'll leave it to you to find the other two that make up the diamond of Virgo on the right-hand side. And if you can't find it, that's okay, because you're just drawing shapes in the sky. All the constellations are just shapes, and they're made up by somebody. And so the diamond of Virgo is another thing that somebody made up. So if you can't find it, then make, I don't know, the toaster of Virgo, or the trapezoid, or the jigsaw puzzle of Virgo. So.
Love it. Thank you, Matthew. Joe Malek asks, do I need to be a straight A student in physics and math to become an astronomer? I know my 9-year-old wonders that same question.
Thank goodness, no. So I was not a straight A student. I did pretty well in math and physics, but in high school, I struggled with geometry. In college, I struggled with some of the other mathematics courses, the really advanced ones. But so the point is that math is the language of astrophysics. And so you have to be fluent in that language. Doesn't mean that you have to be the Shakespeare of mathematics, of that language, but you do need to be very good at it. And so the rest you can sort of get by with. So I know that there are chemists, so those aren't physicists, who do astronomy. And there are even geologists who do astronomy. They do plate tectonics on other planets. In fact, the University of California Observatories has more staff than astronomers. So if we had a little fight between the staff and the astronomers, we'd really be in trouble, because there are engineers, there are computer programmers, we have technicians, we have telescope operators, we even have media specialists. So all of those people are doing astronomy. They're all helping us discover new things. And once we discover those new things, we have to get that information out to the public. So there's more than one way to be an astronomer and do astronomy.
I love that point, Matthew. I've always loved astronomy, and I did not major in any sciences in college. So it's an absolutely delightful opportunity to get to work with all of these astronomers and get to contribute to these really cool discoveries in my own personal way. Okay, we have Bees I-89 in our social media channels. Ask Bees I-89, you know who you are, asked, how can the surface temperature of planets or stars that have not been visited by probes be determined? And related, sort of, how is it determined what a planet or star is composed of?
Well, thank goodness you don't have to visit another star to study it. And so the real question is, how do you do that? So astronomy is a really bad laboratory science, right? So you're not going to make a star in the laboratory, and thank goodness you're not going to make, or you better not, make a black hole in the laboratory. So how do we study these things? Well, we study them from the information that they give away. And in large part, that's mostly photons. And so if you close your eyes and imagine a cast iron frying pan. And so if that cast iron frying pan is in the living room and your eyes are closed, or it's a dark room, sorry, it's a dark kitchen and you have the cast iron thing there, you're not going to be able to see it. But if you put it on the top of the stove and put a little bit of heat on it, in a dark room, you still may not be able to see it, but your skin could feel it. Your skin could detect the radiation coming off of there. You could detect the infrared photons coming off of that frying pan. And you increase the temperature a little bit, and then you might start to see it glow a little bit red. So that's probably not as hot as you really want to take a cast iron frying pan. My wife would be very angry if she found out I made my frying pan glow orange. But then you can start to see it with your eyes. And now if you take that frying pan and imagine instead, put it in a blast furnace, what color would it become? It would become kind of a glowing white. So the color of a star tells you something about the temperature of that star. So that's sort of the lowest order of doing spectroscopy, which is really, that's what I am. I'm a spectroscopist. That's my specialty, is studying stars using the spectrum that they give off. So and really in astronomy, we're usually talking about gases. And so each gas, when you heat it up, depending on the temperature that you heat it to, it has a fingerprint. That fingerprint changes a little bit if you change the temperature, but it's still unique. So a 10,000 degree bit of hydrogen looks a little bit different than a 4,000 degree temperature hydrogen atom. But you can both tell that they're hydrogen. The tricky bit is when they're all mashed together. You've got iron atoms and hydrogen atoms and helium atoms. You put them all together, it becomes tricky And that's where the science and the instruments come in to be able to see the gas. But you start picking out and saying, oh, that looks like the fingerprint of hydrogen at 10,000 degrees. And oh, look, and if it is 10,000 degrees, I bet that's iron's fingerprint there in the spectrum. And then, okay, if I now am convinced that it's 10,000 degrees, what other things are hiding under those fingerprints? And so you sort of dig a little deeper and you say, oh, I can see other things. So that's how we sort of do spectroscopy in astronomy, is we take a spectrum and then pull it apart like a detective looking at a fingerprint.
That's fantastic. Can you tell us a little bit about some of the instruments that we're creating for the future so that we know more, even more about the exoplanets that we're discovering on an almost daily basis at this point?
Right. So it gets tricky if you want to take a spectrum of a planet, because unless it's a free floating planet out there, not next to a star, you know, a planet generally doesn't give off much of its own radiation. Some it gives off a little bit, but not very much. And so if you put that planet right next to a star, you can hardly see it. So what we're trying to build are very advanced instruments that can block the light of the star and zoom in very close to that star using adaptive optics, which we had our director gave a talk last week about adaptive optics. And she explained all about how that kind of system works. And so if we could, we'd love to be able to take a fiber optic cable and take a spectrum of that planet and say, okay, what can we tell about the gases? What temperature is it? And what is it made out of? Do you see helium? Do you see iron? Or do you see things like water or methane gas or some other interesting gas? So that's what we're really after, is making more advanced spectrographs to go after really interesting things like trying to take a spectrum of a tiny planet right next to a great big bright star.
Interesting. Okay. The next question that I have comes from Ava, age 5. Why do stars change color when they get older?
Okay, so stars are all about equilibrium. It's the pull of gravity versus the energy that's pushing out. So gravity is always trying to push it in, and to stop it, energy has to give out. And one of the types of energy that goes out is when the star is born, is that it's hydrogen fusion. It's hydrogen atoms being burned in the center of the star, and then those energetic photons go and work their way out and they support the star. So it's in equilibrium for most of its life. And then towards the end of its life, it starts to run out of gas in the center. There's no more hydrogen to burn. And so the center part starts to collapse on itself, and that releases energy for a short period of time. And that energy goes out and makes the outer part of the star puff up and becomes a red giant. And as it puffs up, it cools. So it becomes red and cool. So a normal star, most stars like our sun, when it starts to run out of gas in the center, then it will puff up and become a red giant. So thankfully, that's a very slow process, and it's going to take about another 4 billion years for it to happen for our star. But in general, that's what most stars go through. Now, sometimes stars can do another cycle. They can find another equilibrium. Instead of burning hydrogen in the center, they can burn something else like helium. But that's another story.
The first question that we received almost immediately when we put up information about this brand new program was from the Gray family. Their 10-year-old wants to know, what is the star closest to death? And when is that star's predicted death? Is that something that we're going to get to see?
Oh, okay. So the question is the star closest to death? is probably going to be Eta Carina. Eta Carina is a star that's kind of a long way away, but it's a huge star. But unfortunately, it's in the southern hemisphere, which means that if you live in Australia or South Africa or Chile, then you could see that star right now. But when I say it's going to blow up right away, what I really mean is the next 100,000 or so years. So, 1 in 100,000 chance that maybe we'll catch it this year. So that's not great odds, but I bet other people have heard that Betelgeuse, which is a star in the constellation Orion, has been changing its color. And so maybe they think, oh, maybe it's going to blow up. So it's a lot closer and brighter, and you can see it from the northern hemisphere. But all of that we know about those stars, all our best models say that probably in this next million years that it's going to blow up. So there's more like a 1 in a million chance that it's going to blow up this year. So if you're going to, like me, live another 70 years, so then you have a 70 in 1 million chance of seeing Betelgeuse blow up. So my friend Alex Filippenko at Berkeley, he studies, he's a supernova hunter. He studies stars that blow up. He's not that patient. So he doesn't want to wait and have that very low chance to happen. So what he has to do is he has to search millions and billions of star systems to look for them. And so usually that means he goes and looks at nearby galaxies to see one blow up. The last one to blow up that you could see with your naked eye happened in the southern hemisphere in 1987. And so that happened in a nearby galaxy called the Large Magellanic Clouds, which you can see with your eye. And it blew up and became just visible to the naked eye from a, okay sight. So it's a very rare event. So if it does happen, you should definitely get away from the city, go out and look at one if they become bright enough to see.
Wouldn't that be something?
It would be.
All right. Well, I've got a couple of related questions. One from David Druin on Facebook and one from Siddhar in the chat here. The first question, and then I'll ask sort of the related question afterwards, is there an opportunity for amateur astronomers to get involved in meaningful research projects? Are there any research projects that can use observations and measurements made by the amateur astronomer using moderately sized and equipped setups? And then the related questions are, are there classes that folks who are amateur astronomers but do have some experience, they're not beginners? Are there classes in the UC system or elsewhere that folks can take if they're interested in learning and even more and being involved in research?
All right. So it used to be that almost all astronomers were amateur astronomers. They were not paid to do their work. They did it for their passion. And then universities kind of came along and some people started being paid. But a lot of results were still discovered by amateurs. So as the telescopes of the professionals have gotten bigger, they've looked out deeper and deeper and deeper into space. And so the smaller telescopes sort of can't compete with that deep look. So what they have to do is compete with where the astronomers can't look. So they either can't look all the time, or they can't look very close to the sun, or they can't look, and they don't want to look at the full moon. So some of the things you could do, for example, are look for comets. Comet hunting is often done very close to the sun. So at the twilight hours, looking for things that are just appearing in the twilight morning. So that's comet hunting. You can do lunar impact flashes. This is really cool stuff. If you take lots and lots and lots of pictures of the moon, particularly a full moon, sometimes you see a meteor impact, bang, hit the moon. So we don't know much about meteor impacts on the Earth because we're sort of too close to it. But you can study it on the moon and see what it looks like for things hitting the moon. And we can study the direction they come in, how big the flash is, how much they explode when they hit the ground. And so almost all of those impact results, or a lot of them, are done by amateurs. Probably the most exciting things that gets any press at all about amateur work is the help that the planet hunters need for looking and following up on planet transits. Sometimes they find planets by watching a star, and then if the planet comes right around and boop, it dims the light of the star a bit for just a short period of time. And then you have to wait a full year or 90 days or whatever the period is until it happens again. So they have these that happen once or maybe twice, and they want to follow up and see, okay, what was the period of that? Was it really a year, or was it half a year or a quarter of a year? You know, did they miss the other events? And so they need people to follow up all of those candidates. And so there's a lot of work that some amateurs have gotten into groups doing to follow up to try to catch those eclipses, those planets going in front of their stars. So if you want to find some of those organizations, you can look, if you were to Google pro-am, like pro amateur collaboration for astronomy, and then you would probably find a lot of hits about organizations that do that. If you want to learn more how to do very sophisticated and quality measurements with your telescope, you could probably take a class. So some of those classes are groups that teach you are your local club. So in Santa Cruz, we have the Santa Cruz Astronomy Club, which I've gone to. And then those groups get together, like all of Northern California gets together, and all the clubs meet. Then they share information, they teach each other, they compare their telescope to your telescope and see what they can improve. Another way you could do is occasionally organizations like University of California Observatories, Lick Observatory teaches a class using a big telescope for amateurs, which is one of our smaller research telescopes, to learn to take pictures, how to analyze those pictures, and how to get information out of them. So that's what I would suggest.
Thank you, Matthew. And thank you to Jim Grubb. If you all look in your Zoom group chat, Jim Grubb has posted the NASA Exoplanet Watch and the link there for everyone to be able to access.
Nice. Thank you.
We are getting ready to enter our lightning round. We're nearing the end of our half-hour session. If you haven't had an opportunity to have your question answered and it's not part of our black hole lightning round tonight, then you can post a question beginning now on UCO's, UC Observatory's Facebook page, our Twitter account, or Lick Observatory's social media accounts as well. You can also email social@ucolick.org, which I'll put that email address up on the screen as we end this session. Matthew has asked specifically for something resembling a bell. So what I've got is here, lightning round, Matthew. 1 minute each to answer these black hole questions. Are you ready?
Well, let me preface to say I'm not a black hole expert. I'll see what I can do.
Just had a lot of black hole questions this time around. So let's see what we've got. All right, Marlene Fretz asks, basic question. How do we detect black holes with radio waves if nothing can come out?
So you can't detect black holes directly with radio waves. What you have to do is detect the stuff falling into them. So a radio tower on the Earth makes a radio wave by sending electricity up and down and up and down and up down the tower, and that produces a radio signal. And in a black hole, there's gas swirling down inside of it. And so that gas gets hot and breaks off all the electrons, and then you have electrons going around in a circle and a circle and a circle. So that emits a radio wave. And instead of being like a tower, it goes in every direction, it goes in only two directions and kind of zooms out that way. And so you can detect massive black holes with radio signals, just like you do with a radio tuner on your radio.
Fantastic. Deepa asks, I think Deepa's on again, how can a black hole move when it is nothing more than a very dense part of space?
So the best part, or the most well-known part of a black hole, is that it is massive. So it's made of matter. And so if you have a black hole over here and then you have another black hole over here, the force of gravity between them still attracts each other. So they still pull on each other. So that's one of the best properties, the best known properties of a black hole, is its strong pull with gravity. And so if you have a small black hole here and a big black hole here, they both pull on each other. So the small black hole moves faster or more towards it, and the big one moves just a little bit. And so they can sort of move down towards each other, and they can actually swallow each other.
Yikes. Hopefully not anytime soon, right, Matthew?
Not nearby.
Not nearby. Okay. Alec Dara Abrams asked, aside from, say, associated galactic distribution, does a massive black hole show any evidence of its past merging history? So do we see the results of those merges?
Right. So a black hole tells no secrets. So black holes only have a few properties. The most well-known one is how big they are, how much mass they have. And so if it swallows up a star, that black hole gets just a little bit bigger, but there's no evidence of that star after it's gone in, after it's been swallowed, there's no evidence of it. So if a black hole swallows another black hole, it gets more massive, it sends out radiation in gravity waves. Those gravity waves can be detected, but once the merger has happened and the event is over, then the black hole tells no more secrets. All it does is say, this is how big I am. I used to be smaller, maybe, but right now I'm this big. And that's the only thing we know.
Mark McKeeve asks, what's inside ultramassive, supermassive, star-sized, and microscopic black holes?
So all black holes are made of matter. Matter gets sucked in or gets pulled in and gets swallowed by the event horizon and then disappears from effectively our universe. So all black holes are made of the same thing, which is matter that have mass. But beyond that, there is no difference between an ultramassive, the biggest black holes at the center of galaxies, and microscopic black holes that might have been made at the birth of our universe. Tiny little black holes smaller than the mass of the moon, say. There's no difference in what's inside because those things are outside of our effective universe. We can't detect them. There's no way to know any other properties inside them. So they're all made of matter. They're all the same things.
Can ultramassive black holes suck in dark matter?
Yes. So dark matter is a label that we give to an unknown property of our universe, which seems to be, when we study our galaxies, there seems to be matter missing. We call that matter that's there dark matter. And we kind of model what some of those properties are, like slow moving. It's not moving at the speed of light, it moves slowly. So if some of that mysterious dark matter happen to fall or get close to a black hole, they do interact gravitationally. And so a black hole could pull in dark matter.
Last question for tonight. How do you tell the difference between the merger of a black hole versus neutron stars that we've heard about before during these conversations?
In 1 minute. Okay, so when neutron stars merge or black holes merge, they release gravitational energy, ripples. So if the universe were a flat pond and you drop in a heavy thing like a big rock, it makes ripples. If you throw in a light thing like a neutron star, like a pebble, it makes small ripples. So when we listen for those ripples, we're hearing the frequency of them is much larger. And so I think last week the director was talking about the whoop that you get when two black holes merge. Well, when neutron stars merge, they get a and it goes on for about a minute. And then right at the end, there's a little whoop. So it's a much longer event.
Well, now that we've worn out our astronomer, I want to thank everyone again for joining us for University of California Observatory's virtual event series.
So who's your next victim?
Our next victim is next Monday at 4 o'clock, starting at the same time. It's going to be another living room lecture. You'll see that we're going to be alternating between the living room lectures and the Ask-an-Astronomer. Dr. Andy Schemer from University of California, Santa Cruz will be talking to you more about what we heard from Matthew during the first question. How do we actually see these exoplanets and how do we characterize what they're made of? Him and his team here at UC Santa Cruz are developing an instrument for Keck Observatory so that we can do just that further and further away and more often, faster, more efficient for our future of exoplanets in hopes that by the time one of the 30-meter telescopes that are being looked at across the world come online, that we have an instrument that can help us to identify life outside of planet Earth. Thank you all again for joining us. If you'd like to be part of the FOLO Family Dinner Series, then you can join FOLO. Any questions that you have for any of these events, but especially for Ask an Astronomer, join us on social media or contact social@ucolic.org for more information. Thank you so much for joining us, and I hope that we see you next Monday at 4 o'clock.
Bye-bye.